In this video, we're going to discuss how to calculate standard deviation by hand, and we're also going to take a look at the differences between calculating the standard deviation for a probability distribution versus using a data list. First off, what is standard deviation? Standard deviation measures the consistency of all of the values in a data set. So the higher the standard deviation, the more inconsistent or the more variable the data is from the mean. The lower the standard deviation, the more consistent it is. The standard definition of the standard deviation is the average distance of every single value from the mean. So think about it. The higher that average distance is, the further each value is going to be from the mean. So let's take a look at these two data sets where I'm giving you the mean and the standard deviation of two different tests, let's say. The mean on each of the tests is 70. But their standard deviations are different. So we always know that the mean goes dead center of the normal distribution. So for both of these, I'm going to put 70 dead center. Now, to calculate the percentage of the values that we anticipate, to calculate the range of the values that we anticipate 68% of all students to have scored in, what we have to do is add one standard deviation above. So 70 plus 1 times 5 would be 75. To get the lower end of that range, we're going to subtract 70 minus 5, which is 65. This tells me that 68% of the values for the people in this class who took the test scored between a 65 and a 75. Continuing on, if we went 2 standard deviations out, now we're taking 70 and adding 2 times the standard deviation. So that would be adding 1070, which is 80. Going to get the lower end of the range, we're going to subtract 2 times the standard deviation, which would give me 60. This tells me that 95% of the people in this class scored between a 60 and an 80 on the test. And the last step would be 3 standard deviations out. So we would add 3 times the standard deviation, which would be 15. 70 plus 15 would be 85. Going 3 standard deviations below to get the lower end of that range, we would get 70 minus 15, which is 55. So we can say now that 99.7% of all people in that class scored between a 55 and an 85. Similarly, if we look at the distribution on the right, we have a different class, and now we have a standard deviation of 10. So 70 plus 10 gives me 80. 70 minus 10 gives me 60. So 68% of the people in this class scored between a 60 and an 80 on their test. And then if we finish calculating it out by adding 2 times 10 to give me 90, and subtracting 2 times 10 to give me 50, and then lastly, adding 3 times 10 to give me 100, and subtracting 3 times 10 to give me 40. Taking a look at all of these values, taking a look at, let's say, 1 standard deviation away, in class 2, this class right here, you see that the values are a much wider range than we have in class number 1. So because the standard deviation was higher, there was a bigger range in terms of the middle 68% of all the students who scored in the class. So just keep in mind, the bigger the standard deviation, the more variable the data set is. And the lower the standard deviation, the more consistent the variable is. So we have 2 different types of problems that we can come across here. We have a data list and a probability distribution. Now, how do you know which is which? And it's important to know which is which because they use different formulas to calculate that standard deviation. So at number 1, you can see that they actually just give you P of X, which means the probability. As soon as you see that, you know that you have to use the certain formulas that we discussed. In number 2, there is no indication of probabilities anywhere. It's just a list of numbers. So that's another set of distributions as well. Now, whenever we do the probability distribution, there's going to be times where I give you a box or a table that looks just like this, or there's going to be other times where I ask you to calculate explicitly the probability distribution and all that stuff. So keep that in mind as we go through. There's a difference in terms of the formulas, and here they are. If you see something with a probability distribution indicating that there's some probability going on there, we actually use mu for mean. That's the generic term, no matter what kind of distribution you're dealing with, probability or data list alike, we use that mu to indicate mean. Now, for probability distributions, we talked about expected value. They're the same thing. They're both the mean. All right, so you can actually, use mu or E of x and you're considered correct. All right, and the formula to calculate the expected value or the mean for a probability distribution is the sum of each x value times its corresponding probability value. And its standard deviation is the square root of the deviation squared times its probability. In the data list, this is the old school method of how you're going to calculate mean. You sum up the values and divide by the number of values in the data set. The standard deviation, we're going to take the sum of the deviation squared and divide by n minus 1. So the number of values minus 1. So in number 1, we see that we have x and p of x, which means that it's a probability distribution. So in order to make sure that we can continue, we have to make sure that we have both conditions satisfied. Are the sum of the probabilities equal to 1? Well, we add 0.4 plus 0.2 plus 0.1 plus 0.3. That does equal 1. Therefore, that condition is satisfied. And we also have to check if each probability is between 0 and 1 inclusive. And we take a look, and there is no value that's less than 0 or greater than 1. So that is also satisfied. So since we have our two conditions satisfied, now we can go ahead and find the mean, the variance, standard deviation, and so on. The steps to calculating the standard deviation for a probability distribution are as follows. I highly recommend that you pause, copy these down, and then press play when you're ready to keep going. So number 1 is to calculate the expected value or the mean for the probability distribution. Number 2, you're going to take each x value and subtract the mean to get the deviations. Remember, deviation is x minus mu. Then you're going to square each deviation. Remember how we talked about in class, this will get rid of the signs with an operation that can be undone later on. Absolute value is absolutely out of the question because that changes the definition of the number, and taking the absolute value of a number can never be undone. Number 4, you're going to multiply each squared deviation, so x minus mu squared, by its respective probability. Then you're going to sum up the values that you get in step 4 to get the variance. Remember that variance is standard deviation squared. So of course, to get the standard deviation, we have to take the square root of step 5 in order to get the standard deviation. Remember, this puts the measure back into the units that we are working with. So let's get started with number 1. We're first going to calculate the expected value. So we take each x value and multiply it by its probability. So we have negative 3 times 0.4 plus 2 times 0.2 plus 1 times 0.1 plus 0 times 0.3. This gives us an expected value or a mean of negative 0.7. So now the mean is calculated. That's step 1. Now taking a look, the next step is to take each of the x values and subtract that mean. So we're going to take negative 3 and subtract our mean, which was negative 0.7, and that's going to give us negative 2.3. We continue on and do this for each of the x values, and we get this list here. The next step is to find my deviations. So we just calculated the deviations by taking each value and subtracting the mean. That's basically how far each of these values are from the mean. So for instance, negative 3 is 2.3 below the mean. 2 is 2.7 above the mean, etc. The next step is to take the deviations and square them. So basically, I'm going to take each value in this list and square it to get my deviation squared. So negative 2.3 squared is 5.29, 2.7 squared is 7.29, etc. The next step is to take a look at that variance formula. Variance is standard deviation squared. And remember that variance is just the step to get us to the standard deviation. The units of a variance is pretty useless because it gives us our answer in units squared. So I'm going to take the sum of the deviations, each deviation, times its respective probability, and get a new value for it. So the next step is I'm going to take each of these deviations and multiply it by its respective probability. Now, taking a look, we're still dealing with x value -3. So its respective probability of the deviation squared of -3 would be 0.4. The probability of 2 was 0.2. So remember that you're finding the respective probability of the x values when you are multiplying your probabilities. So we calculate each of these out and get values for them. The next step is to take each of these values, which is x minus mu squared times its probability, and we want to sum them up. This is going to give me my variance. Notice that variance has units squared. So in order to be able to create my bell curve and understand what it means in the context of the problem, we have to take the square root of both sides. Remember that the standard deviation is equal to the square root of the variance. All right, so we take the square root of 4.01, which gives us 2.00250. Remember, 3 significant digits. So now we create our bell curve, and just like we went over at the beginning of the video, we take our mean and put it dead center. Now our mean was our expected value that we had calculated first step, and then I add one standard deviation. So I add 2.0025 to -0.7 and it gives me this value. And then I subtract one standard deviation to give me -2.703. That tells us that 68% of the values in this context will fall between -2.703 and 1.303. 95% of the values will fall within 2 standard deviations, which is -4.705 units and 3.305 units. And lastly, 99.7, so almost all of the values will fall between -6.708 and 5.308 units. So the last step is to deal with your interpretations. So we have our calculations that we've gone through up there. Here's the bell curve that I've created. Now, since this is a probability distribution, notice that we're talking about an infinite number of trials. We don't know how many trials are going to happen. We are looking over infinity here. So if there were an infinite number of trials conducted, there would be an average of -0.7 units per trial. Now, of course, you have to put this in context. So if there were an infinite number of trials conducted, are you playing a game? Are you flipping cards? Are you rolling a die? That's the information that would go in that spot. And then, of course, you would want to talk about the units here. So is it dollars? Is it dots? Is it dogs? And then per trial, per turn, per player's turn, per household, depending on the context of the problem, you want to fill all those blanks in. This is kind of a generic way to interpret the mean. The next step is to calculate, or we have the standard deviations calculated, and the way that you would interpret this is 68% of the trials would fall between -2.703 units and 1.303 units, and you do that for each of the 3 percentage values that I said were important. Again, you would want to put this in context. If we were talking about, money on hand here, we found the probabilities of each of the amount of money on hand, or something along those lines, how much money you could win, whatever. You would say that 68% of all the people would fall between losing $2.70 and winning $1.30. Just make sure you put it in terms of the context that you're dealing with. Make sure that you know how to interpret each of these. All right, number 2, this is a totally different situation here. There is no indication of probability. We actually know the number of trials. We just count the number of numbers that are given to us. All right, so in this case, since there's a counted number of trials, we know that this is a data list. I would say to pause the video now, copy down the steps, and then when you're ready, you can press play. Okay, so you want to find the mean using the old school method, the method that everybody already knew before coming into this class. Since there's no probabilities present, then you're going to subtract the mean from each x value to find the deviations. Step 3, you'll square the deviations to get rid of the signs. Number 4, you'll calculate the sum of squares, which is the sum of the squared deviations. Number 5 is to divide by n-1 to calculate the variance. And number 6 is to take the square root of the variance to calculate the standard deviation. So I add up all the values to get me 69. there are a total of 10 values in the data set. There are 10 numbers here. So I divide by 10, which gives me 6.9 units, since this is a generic example. The next step is to take each value in the list and subtract the mean, which we found to be 6.9 units. The next step, so we take 8 and we subtract 6.9, which will give me 1.1. Take 7, subtract 6.9, which gives me 0.1, etc. You do that for each value in the list. Now, if you were to add up, in this case, since there's a counted number of trials, if you were to sum up the deviations here, it would always equal 0. It doesn't happen like that with the probability distribution because they're weighted. Don't worry so much about the specifics of it, but it's always a good check to make sure that when you have a data list, the sum of the deviations equals 0. So we can't find an average if it always adds up to 0 because of the signs. So what we want to do is neutralize all the signs to make them positive in a way that can be undone. So we take each of the values of the deviations and we square them. So 1.1 squared is 1.21. 0.1 squared is 0.01. To find the variance, we take the sum of squares. So the sum of this list is the sum of squares, which will give us this value up here. So I take 1.21, add it to 0.01, etc., all the way down into the last value, and I divide by the number of values in the list, which was 10 minus 1. So we have 50.9 divided by 9, which gives us 5.656 units squared. Again, this is giving us the variance. The last step is to take the square root of both sides so that you can get it in terms of the units that we've been dealing with. So standard deviation is 2.378 units. We calculate this, the standard deviation bell curve in a very similar way that we did in the beginning of the video and also with the probability distribution. The only major difference here is the way that we interpret the mean, which I'll talk about in just a second, and the way that we calculate the standard deviation. The formulas are different, but in terms of it, there's a lot of similarities to be drawn here. All right, so again, we have the mean, which is dead center. Then I add 1 standard deviation to get my 68% range and subtract 1 standard deviation to get the lower end of it, 2 standard deviations to get the 95 range, and 3 standard deviations away to get me my 99.7% range. Now, pay careful attention to the difference in the way that the mean is interpreted for a list of values versus the probability distribution. Remember that the probability distribution, this is all theoretical. You know, we don't know exactly how many trials are there, so we always talk about infinity. Whereas here, the mean is more finite. We only have 10 numbers. That's our sample, and that's that. So we just say that the average of the sample is 6.9 units. This sample of 10 numbers. This is a finite distribution as opposed to the probability distribution, which is kind of like infinite and theoretical. There aren't a set number of trials to be drawn. All right, and then the way that we interpret it is exactly the same as the way that standard deviation is exactly the same as the way that we did it for the data list. So 68% of the trials would fall between 4.5 and 9.3 units. 95% would fall between 2.1 and 11.7, etc. And that concludes how to calculate standard deviation by hand for both a probability distribution and a list of values.